Well, we're now moving into Chapter 14A, which is probably one of the two feared chapters in this textbook, which is Data Analysis, Descriptive Statistics. Well, statistics. What do you need to know? Well, you need to know about the meaning of statistics, you need to know about the use of statistics, and you need to know about the limitations of statistics. What you do not need to know are the calculations. There are two key concepts related to statistics. Choosing the appropriate data analysis method in research is as important as implementing the right nursing intervention in practice. And two, just as a surgeon cannot learn surgery in 9 easy lessons, you cannot learn statistics in just this lesson. Now, before we begin our discussion about descriptive statistics, I need to go over levels of measurement. Levels of measurement is the assignment of numbers to objects or events according to rules. The levels of measurement are the determining factors of the type of statistics to be used in analyzing data. Now, the first level of measurement we're going to look at is nominal measurement. This is where variables are broken into 2 or more categories, and they're assigned just arbitrary numbers. The numbers have no rank order, no sense of one category being ranked a higher level than another. The categories are mutually exclusive, meaning the object either has a characteristic or it does not. The numbers assigned to each category are nothing more than labels. They do not indicate more or less of a characteristic. Examples include sex, hair color, marital state, religious affiliation, or blood type. The only mathematical operations that can be done with nominal level measurements are frequencies and percentages. The next level of measurement is ordinal. This measurement reflects a rank order among the categories, but we do not know how much greater or less than one category is from another. This ordinal measurement provides more information about variables and characteristics to be measured. The numbers assigned to each category can be compared, and a member of a higher category can be said to have more of an attribute than the member of a lower category. Ordinal data are limited in the amount of mathematical manipulation possible. They can do frequencies, percentages, medians, percentiles, and rank order coefficients of correlations. An example would be disease staging in cancer, stages 1, 2, 3, or 4. Although we can safely say that stage 2 is worse than stage 1 and better than stage 3 or stage 4, we really don't know by how much. Now, interval measurement are where the categories are made up of real numbers that allow us to order the numbers and know the distance between those numbers. The intervals between the categories are equal. Interval data consist of real numbers, and as I said before, the real numbers are the category. The data, or numbers, can not only be placed in categories, but also the distance between the ranks can be specified. For example, if body temperature were being measured, a reading of 99.0 might be one category, 98.6 might be another category, and 98.2 could be another category. The researcher would be correct in saying that there is a 0.4 difference between the first and second category and between the second and third category. The researcher could even go one step further and find the average reading of the temperatures. Now, the last level of a measurement that we're going to consider is ratio measurement. Ratio measurements have the same properties as interval data, except the measurement scale for the variable possesses a meaningful zero. This means that when zero is reached on the scale, the variable is absent. All mathematical procedures can be done on data from ratio scales. So where does the classification lead us? The important distinction is between nominal and ordinal variables on one hand, and interval and ratio variables on the other hand. It makes no sense to speak of the average value of the sex of a sample. However, it is sensible to speak about the average blood sample or an average height of a sample of patients. A helpful strategy is to use instruments that result in the highest level of measurement possible for the variables of interest. Data measured at a higher level can always be reduced to a lower level, but the opposite is not true. More information can be performed using exact patient age and years, and the data can be subsequently collapsed into age groups for other presentation purposes. But if the data are collected only in terms of age category, the application of certain statistical procedures is not possible. In other words, you always want to collect your data at the interval or ratio level of measurement. Well, you're going to find that there are two categories of statistics. There's descriptive statistics, which we're talking about in this lecture, and there are inferential statistics, which we're going to talk about in the next lecture. Descriptive statistics are also referred to as summary statistics. In any study in which the data are numerical, data analysis begins with descriptive statistics. In simple descriptive studies, the analysis may be limited to descriptive statistics. So, remember, every study has at least descriptive statistics and is usually concerned with the sample. Okay, so now you have a bunch of numbers. Now what? Well, whether a study involves 10 or 10,000 subjects, eventually the researcher ends up with a collection called a database. In the case of nominal or ordinal variables, the numbers are some indicator of the category to which each subject belongs, for example, sex, religion, or diagnosis. For interval and ratio variables, the number will have the actual numerical value for each subject, for example, the height, blood pressure, or number of drinks per day. Data that are not analyzed or organized are overwhelming. It is not possible to discern general trends until some order or structure is imposed on the data. Frequency distributions represent one method of imposing some order on a mass of numerical data. They are a systematic arrangement of numerical values from the lowest to the highest, together with a count of the number of times each value was obtained. A histogram is another common graphic way of presenting data. Histograms are especially important because they show the distribution of the data. Generally, there is a construction made to represent a set of scores after we have completed a frequency table. The standard format for a histogram usually involves a vertical scale that delineates frequencies and a horizontal scale that delineates values of the data being represented. And there are bars in the table representing all of the data. Although a frequency distribution is a convenient way to summarize data, it has certain disadvantages. It is difficult to compare two distributions derived from different samples because the information is buried in the number of responses in each category. It is also tedious to draw graphs and a lot easier to get the computer to spit out a series of numbers. As a result, some way to summarize information is necessary. The conventional approach is to develop methods to describe where the center of the distribution lies and how wide it is. These are the measures of central tendency. Frequency distributions are an important means of organizing a set of data and of clarifying group patterns. In many studies, however, a group pattern is of less interest than an overall summary of the sample's scores. The researcher usually asks such questions as, how satisfied is the typical patient with his/her nursing care? Or, how much fat does the average American consume during the holidays? These questions seek a single number that best represents a whole distribution of measures. To laypersons, this is the average. There are actually 3 indices that statisticians use: the mode, the median, and the mean. This is an example of a frequency distribution. You can kind of think of it as on the horizontal axis are the number of weeks that you've been collecting data, and on the vertical axis it'd be the percentages of your patient satisfaction scores. And you can see that in weeks 1, 3, 5, and 7, your percent of satisfaction was about 60%, but then it dropped way down in week 8, and it's been kind of up and down all the rest of the time that you've been collecting data. Now you can make some inferences from all that data that you collected. Now we're going to look at the mode. The mode is the numerical value or score that occurs with greatest frequency. In this data set, the number 5 appears 14 times and is the mode. The mode, in other words, identifies the most popular score. The mode is relatively infrequently used, except for describing typical values on the nominal level measures. Researchers may use it to describe characteristics of their samples. For example, in a research study, it might say, the typical modal subject was a white female, unmarried, living in an urban area, and of a Catholic background. It also tends to be the most unstable, meaning that modes fluctuate widely from samples drawn from the same population. Now, the median is the value in the exact center of an ungrouped frequency distribution. It is obtained by rank ordering the values, and this is something else to consider. When the number of values is uneven, the median may not be an actual value in the data set. The median is the exact point in a distribution above which and below which 50% of the cases fall. Now write down the following numbers: 2, 2, 3, 3, 4, 5, 6, 7, 8, and 9. The value that divides the cases exactly in half is 4.5, which is the median for this set of numbers. The point that has 50% of the numbers above and 50% below is halfway between 4 and 5. An important characteristic is that the median does not take into account the quantitative values of individual scores. The median is an index of the average position in a distribution of numbers and is insensitive to extreme numbers. For example, if you replaced the number 9 on the end of your first distribution and put 99 there instead, despite the fact that the last value increased from 9 to 99, the median remains unchanged at 4.5. Because of this property, the median is often used when the distribution is skewed and when one is interested in finding a single number. A median may be calculated for ordinal or higher level data. So now we're going to look at the mean, and that is something that you're probably very familiar with. The mean is the sum of values divided by the number of values being summed. Like the median, the mean may not be a data set value. For interval and ratio variables, we can use the modal and the median values, but we can also use a much more common sense approach, simply averaging all the values. The mean is the statistical jargon for the average obtained by adding up all the values and dividing by the total number of subjects. The symbol X with a line above it, pronounced X bar, is used in research reports to signify the mean. The mean is the center of the distribution in the sense that the total amount by which someone's scores in the distribution are greater than the mean is equal to the total amount by which the other scores are less than the means. But you must use caution, caution, caution. Caution should be used when a distribution exists that contains one or more extreme values, especially when the data set is small. The mean will be moved toward the extreme value and will not represent the average distribution in terms of being a typical score. Okay, so write these numbers down: 21, 23, 23, 26, 28, and 82. Now each of those numbers represents the number of days in which a patient stayed on your unit. And in your hospital, the administrators want to be cutting down on the number of days that a patient stays in the hospital. But you have to go report this data. Well, you could use the data and you could average the numbers. However, the mean is 33.8. Because of that number 82. However, you could report it as the mode of 23, which is going to look a lot better than the 33.8. And as you can see, the mean will be moved towards the extreme score. The mean is the most widely used measure of central tendencies. When researchers work with interval or ratio measurements, the mean is always reported. The mean is the most stable. If repeated samples were drawn from a population, the means would fluctuate less than the modes or the medians. Because of this, the mean is the best estimate of central tendencies. Now we want to look at measures of dispersion, which includes range, percentile, standard deviation, and standardized scores. The various ways of determining the average provide a first step in the development of summary measures of distributions, but we also need some measure of the extent to which individual values vary or differ from the mean. Measures of dispersion or variability describe the scattering of the scores within the distribution. These include the already mentioned range, percentile, standard deviation, and standardized scores. Now the first one we're going to look at is the range, and it's the easiest. It is measured by subtracting the lowest score from the highest score and uses only the two extreme scores. In this example, it's 9 minus 1, which equals 8. It is a very crude measure and sensitive to outliers. For example, if the length of stay for 5 patients is 3, 2, 4, 3, and 5, the range is 2 days. If a patient is added to the group whose length of stay is 12 days, the range becomes 10 days. A common interpretation error is to look at the range and to assume that the scores are distributed throughout the range. As this example illustrates, Large parts of the distribution between the high and low points may be empty. It is also quite possible to have different scores in the same range. A range can be calculated for ordinal and higher level data. The range should always be reported with other measures of variability. Percentile is another measure of dispersion. It represents the percent of cases a given score exceeds. For example, in pediatrics, the nurse uses a percentile to describe the weight and height of a child. A score in the 75th percentile is exceeded by only 25% of the scores. A score in the 25th percentile is exceeded by 75% of the scores, meaning that only 25% of the scores are worse. The mean is the 50th percentile. Well, there's the normal curve. The normal curve is a theoretical frequency distribution. Notice it's theoretical, of all possible values in a population. No real distribution exactly fits the normal curve. However, in most sets of data, the distribution is similar to the normal curve. Levels of significance and probability are based on the logic of the normal curve, and we're going to talk about that in the next lecture. The normal curve has a normal distribution. About 68% of the scores or means will fall within one standard deviation. 95% within two standard deviations of the mean, and 99.7% will fall within three standard deviations of the mean. Now, this is a picture of the normal curve. It has been observed that the natural variation of many variables tends to follow this bell-shaped distribution, with most of the values clustered symmetrically near the mean and a few falling out on the tails. The shape of this bell curve can be expressed mathematically in terms of the means and the standard deviation. In other words, if you know the mean and the standard deviation of your data, then you can assume that the data follow a normal distribution. Then you can tell the shape of your data by putting it in a formula for the normal curve. This is the most important thing about this whole normal curve thing. If your data follow the bell shape, then you may use statistical formulas that are involved in inferential statistics. Well, another thing to know about the normal curve is that there are non-symmetric distributions, where the peak of the curve is off-center. There's a positive skew, which means the tail is longest to the right, and there's a negative skew where the tail is longest to the left. Whatever it is, skew is bad, and you cannot use inferential statistics if your data is skewed. Now, there's the standard deviation. Standard deviation is the measure of average deviation of the scores from the mean. It is intimately related to the mean. It is almost always used as a measure of variability when the mean is used as a measure of central tendency. The more the scores differ from the mean, the larger the standard deviation, and conversely, the less the scores differ from the mean, the smaller the standard deviation. For example, if all scores in a distribution were equal to a score of 25, everybody got 25 on the test, each score would equal the mean and the standard deviation would be 0. If everyone scored between 24 and 26, the standard deviation would be greater than 0, but it would be a small number, less than 1. If half the students scored 0 on a 50-item test and half scored 50, the standard deviation would be large because every score is a long way from the mean of 25. The mean indicates the best single point in the distribution for summarizing a set of values, but the standard deviation tells us how much, on average, the values differ from the mean. In essence, the standard deviation communicates how wrong, on average, the mean is as an overall summary of the scores. In other words, the smaller the standard deviation, the better the mean is as a summary of a typical score. Well, this is a table that shows what you can figure out from the mean, standard deviation, and the range. It talks about health-related characteristics of children with congenital heart disease. And as you can see, the N is the number of children, and in this particular study there were 30. And then it gives you some percentiles. For fetal diagnosis, 6% of them were diagnosed at that time, etc. Now, what I want you to look at is under total hospitalizations, they have a mean of 2.37 with a standard deviation of 1.15. That standard deviation is pretty small, which means that mean represents close to the average stay of these kids, and you can see the range was from 0 to 5. But look at the total number of days in the hospital. The mean says there were 30.57, but look at that standard deviation. It's huge, 22.10. And look at the range. Some kid was in the hospital no days, and another child was in there 106. If you look at cardiac operations, the mean was 2.10, and look at the standard deviation is pretty small. With cardiac casts, the same thing. The mean was 1.157, and the standard deviation is 1.16, and you can see both of their ranges are 0 to 5. Where, look at these outpatient visits since diagnosis. The mean says there were 12.50, and the standard deviation is a little high at 4.82, and you can see the range was between 4 and 28. So both of those standard deviations that are a little bit high give us some information about that mean in this particular study. And this ends my lecture on descriptive statistics.